structuralist point of view is that in set theory, any two different sets play different structural roles. They have a different isomorphism orbit as an internal matter. Now, Tony Martin argued on essentially similar grounds as that there cannot be more than one concept of set, because if we had two different concepts of set, then we could match them up by comparing their cumulative hierarchies. If the two concepts agree up to this level of their cumulative hierarchies, then they would have to agree on the next level, and so on. So there's a kind of similar point made by Kreisel, namely that because the set-theoretic universe is determined in second-order logic by the second-order Zermelo axiom, it follows that, say, the continuum hypothesis has a determinate truth value. The truth value of the continuum hypothesis is determined by second-order logic because it's revealed, the truth value of the continuum hypothesis is revealed in level omega plus 2 in the cumulative hierarchy. Now, critics view that as sleight of hand, really, because to talk about the sort of second-order logic amounts to set theory itself in the meta-theory. And so, according to Kreisel, we have a determinate truth value for CH, but we don't know which it is because, in fact, we don't know which sets there are exactly, and it's amounting to the sort of independence of CH in the meta-theory as a first-order matter. And so, so there's definitely criticisms. Okay, so what is the criteria by which we're to adopt new axioms? And sort of, can we settle the CH by adopting new axioms? Or one should compare sort of intrinsic justification for axioms with extrinsic justification. So the intrinsic justification would be in support of axioms that are in accordance or conformance with our initial concept of set. So we would adopt intuitively clear principles about sets like extensionality and union and pairing set and so on. And maybe even the axiom of choice can gain support from intrinsic support. Because we have an intuitively clear concept of set by which all the possible sets exist, including the ones that make those choices that the axiom of choice is asserting. And so one can find intrinsic grounds on which to view the axiom of choice as true. So we can contrast that with extrinsic justification, by which we judge an axiom by means of its consequences and what you can prove from that axiom, even if maybe we're lacking direct intrinsic support for the axiom. So Gödel had written on this idea by saying famously, there might exist axioms so abundant in their verifiable consequences, shedding so much light upon a whole discipline and furnishing such powerful methods for solving given problems, that quite irrespective of their intrinsic necessity, they would have to be assumed at least in the same sense as any well-established physical theory. And so many of the large cardinal hypotheses fulfill that vision in many respects, precisely because of those regularity consequences of the large cardinal axioms. And many instances of those regularity consequences are observed in practice, so we have independently verified instances of the consequences of those axioms, and so one can view that as extrinsic support for the truth of the large cardinal axioms. Now, Gödel had hoped that large cardinals would settle the continuum hypothesis, but this is now known not to be correct. Using the method of forcing, we can prove that any of those large cardinal notions I mentioned before cannot settle the continuum hypothesis, because we can preserve those large cardinal notions by forcing that either forces CH or the negation. So what is an axiom? What does it mean to adopt an axiom? There's been really a shift in the meaning of that term over the years. So formerly, of course, an axiom meant a self-evident truth. If you have a fundamental theory, then an axiom is a fundamental rock-solid truth about which we don't question. So in geometry, Euclid's axioms are expressing the most fundamental geometric truths. Dedekin's axioms are expressing the central core of our beliefs about the natural numbers. Zermelo's axioms are expressing the fundamental truths about the concept of set. But really, contemporary set theory has become awash with diverse axioms that often stand in conflict with one another. So we have Martin's axiom, the axiom of constructibility, axiom of determinacy, diamond axiom, square principles, large cardinal axioms, ground axiom, and so on. so really the word axiom has come to mean something like a concise fundamental principle whose consequences are to be studied. It's not carrying the connotation of self-evidently true. Now, Pfefferman despairs of this usage. He writes, "It's surprising how far the meaning of axiom has been stretched from the ideal sense in practice, both by mathematicians and logicians. Some even take it to mean an arbitrary assumption and so refuse to take seriously what purpose axioms are supposed to serve." Okay, so on the other side, to my way of thinking, really this new usage arises directly from the case of geometry, where we had the Euclidean axioms, okay, and they had the status of self-evident truths until the discovery of non-Euclidean geometry, of course, tempted us to the alternative incompatible axiomatizations. And so now in geometry, we're considering diverse theories. Each of them has axioms, but those axioms are in conflict with one another. And so we no longer think that there's an absolute geometric truth about whether the, say, parallel postulate is true. Is it a fundamental truth or not? Well, in Euclidean geometry, it's an axiom, but in non-Euclidean geometry, it isn't. The negation is. So rather, the role of the axioms is to identify succinctly expressed geometric assertions that point at the differences in the theory. And so this is the contemporary use of the axiom. So in set theory, we identify clear statements of principles, set theoretic principles that have interesting consequences and that may be true, but we're not asserting that they are self-evidently true. Okay, so we have this vast spectrum of set theoretic possibility because of the independence phenomenon. Practically everything is independent, and we want to know how should we extend our theory so as to add new axioms, and by what criteria should we be using? Should we be doing so? Succinctly expressed geometric assertions that point at the differences in the theory, and so this is the contemporary use of the axiom. So in set theory, we identify clear statements of principles, set theoretic principles that have interesting consequences and that may be true, but we're not asserting that they are self-evidently true. Okay, so we have this vast spectrum of set theoretic possibility because of the independence phenomenon. Practically everything is independent, and we want to know how should we extend our theory so as to add new axioms, and by what criteria should we be using? Should we be doing so? So one of the central unresolved questions that I find to be at the core of the foundational dispute is the question of whether it's better to have strong axiomatic foundation or a weak one. So, for example, you can easily find mathematicians objecting to the replacement axiom by saying, look, we don't need the replacement axiom for most of the development of classical mathematics. So the vast bulk of mathematics can take place in a much weaker axiomatic framework without the replacement axiom, and we can just work in Zermelo's system, or even much weaker. And so is that a good thing to get rid of the replacement axiom, or do we want the axiom system to be as weak as possible or as strong as possible? So Steele argues that the strongest foundations will win out in the end, not the weakest. So he says what is important is just that our axioms be true and as strong as possible. And so from this view, one wants to seek the fundamental principles that will enrich our mathematical knowledge and providing those deep insights. And at the moment, the large cardinal axioms are the strongest known principles in mathematics that we have. So these axioms identify a rich structure theory for sets of real numbers, and that's a structure theory that's not really anticipated by any competing foundational system. And ultimately, Steele argues that those consequences will be the reason that large cardinal set theoretic foundations will endure, because any successful foundation of mathematics would ultimately have to incorporate the large cardinal hypotheses and their consequences in order to explain the mathematical phenomena that flow from those axioms. Okay, so I think, though, this issue about weak versus strong is something that hasn't really been explored sufficiently by philosophers, and I strongly encourage you all to engage with that issue. I think there's quite a bit of room there for philosophical discussion. So Saharon Shelach, in contrast, despairs at the idea that we're going to find compelling new fundamental principles. So he writes, some believe that compelling additional axioms for set theory will settle problems of real interest will be found or even have been found. it's hard to argue with hope and problematic to consider arguments which have not yet been suggested. However, I do not agree with the pure Platonic view that the interesting problems in set theory can be decided and we just have to discover the additional axiom. So he says, my feeling is that ZFC exhausts our intuition except for things like consistency statements, and so for him a proof means a proof in ZFC. Pfefferman argues, on the other hand, that mathematics does not need new axioms. So he writes, I'm convinced that the continuum hypothesis is an inherently vague problem that no new axiom will settle in a convincingly definite way. Okay, let me now finally, I know I'm going way over, let me finally come to the multiverse view. There's an ongoing vigorous debate in the philosophy of set theory. So according to set theoretic pluralism, there's a huge variety of concepts of set, each giving rise to its own set theoretic world. So I've described the situation by writing, as a result, the fundamental objects of set theory have become the models of set theory, and set theory has moved with agility from one to another. Set theory appears to have discovered an entire cosmos of set theoretic universes, revealing a category theoretic nature for the subject in which the universes are connected by the forcing relation or by large cardinal embeddings in complex commutative diagrams, like constellations filling a dark night sky. So the point is that we have all these different concepts of set, and we can construct different models of set theory from one another in order to realize specific set theoretic relations amongst those models, and it's really quite remarkable. In many respects, this is what set theory has become about. So one might hope for a kind of dream solution of the continuum hypothesis. What we really want is a principle that would have intrinsic support, a sort of intrinsically justified principle that also settled the continuum hypothesis. But I have argued that this is now impossible because of our experience with all of these other set theoretic worlds, in some of which the continuum hypothesis is true and in others of which it's not true. And so on the multiverse view, the continuum hypothesis is a settled question. It's incorrect to describe the CH as an open problem. The answer to CH consists of the expansive detailed knowledge that set theorists have gained about the extent to which it holds and fails in the multiverse. Let me also mention the analogy between this multiverse perspective and geometry. There's really a very strong analogy between the pluralist nature of set theory and the established plurality in the foundations of geometry. So for thousands of years, of course, mathematicians studied geometry and thought of geometry as the study of the one true geometry. It had a singularist nature until the discovery of non-Euclidean geometry, and then the singular concept splintered into distinct separate concepts of geometry, and mathematicians realized, hey, the subject is really about these different incompatible concepts of geometry. And it was no longer sensible to ask whether the parallel postulate is true, but rather whether it's true in this geometry or in that one. And similarly, in set theory, it's not sensible to ask whether the continuum hypothesis is true or not. You ask, is it true in this set theory or in that one? So, the term Platonism used to carry decades ago. So I remember when someone would describe themselves as Platonist, they were also intending to express that they believed in the singularist view, in the universe view, that there's a unique final Platonic universe in which set theoretic statements would achieve their absolute truth value. But today that usage has relaxed somewhat, and one should view Platonism as really about mathematical realism. It's about the real existence of the mathematical objects, rather than about the uniqueness of the set theoretic realm in which those objects exist. And in an extreme form, there's the concept of plenitudinous Platonism, Mark Balaguer's view. Plenitudinous Platonism is asserting, it's a kind of Platonism because it's about the real or genuine existence of the mathematical objects, but there's many different models or realms of those structures. Okay, I guess that's it. That's all I had to say. I'm sorry I went way over, and I'm sorry for the technical difficulties at the beginning, but we can open it up for discussion and questions now. Let's see, I see some in the chat, so why don't I address those? Someone says, Oh, okay, let's see. Someone says, what does it mean to talk about models of ZFC? Well, the ZFC is the Zermelo-Fraenkel set theory with the axiom of choice is a first-order theory. We can write down the axioms exactly just similar to the way that we write down the axioms of, say, piano arithmetic, or the axioms of group theory or field theory or whatever. And so it's a first-order theory, and so we have a concept of a model of ZFC. The language is just the epsilon relation, so ultimately a model of ZFC is a set, a domain, with an interpretation of the set membership relation on that domain such that that membership relation obeys the axioms. So it should satisfy extensionality and union and pairing and so on. So when we say a model of ZFC, we just mean a model of that theory, and we can analyze it model theoretically and apply Levenheim-Skolem theorem and so on and do model theoretic constructions with those models. But on the other hand, it's sort of a model of ZFC is also a set theoretic realm, and we can imagine jumping inside that model and living a kind of mathematical life inside that model, because ZFC proves that the real numbers exist and the complex numbers and the topological spaces and so on. All the kind of classical mathematical ideas that you might have are generally provable in ZFC. And so we can imagine living inside that model and having a full and rich mathematical life. And so that's what makes it sort of philosophically robust and satisfying, is that we can, from above, look at those models of ZFC and apply model theoretic methods to construct different ones. And at the same time, we can imagine living inside them and living a kind of mathematical life inside there. I'm not sure if that answers your question or not. Okay, are there any other questions? I'm sorry, I went way over on time. I apologize. Please go ahead and unmute yourself if you have any comments. Can we imagine mathematics without set theory? Well, I can't. No, I don't know. Of course, sometimes when one is considering sort of set theory as a foundation of mathematics, then it's important to recognize that, of course, it's not the only foundation, and there are other foundations, the category theoretic foundations or say type theoretic foundations and so on. And everyone agrees that there are these alternative foundations of mathematics. But that doesn't mean that those alternative foundations, that somehow you don't have set theory anymore, because set theory is also, as I mentioned at the beginning, a mathematical subject. It's a mathematical subject, and it's also serving the role as foundation. There's these two roles. So if you have a different foundation of mathematics, then it should be able to talk about set theory also, because set theory is a mathematical subject. And so any mathematical structural idea that's laying a claim to being a foundation of mathematics should also be able to be a foundation for set theory, because that's part of mathematics. I mean, just in the sense that it's also going to be a foundation for algebra and topology and so on, all the other parts of mathematics. So I'm not sure what you mean by imagining a mathematics without set theory. I mean, of course, there are other kinds of mathematics that don't explicitly engage with set theory. So I can imagine those parts of mathematics, and there's no set theory in those subjects. Okay, what is my intuition of mathematics without a C? Okay, so without the axiom of choice, right? So there's a very rich subject developed studying the nature of set theory without the axiom of choice. There's many papers written in conferences and so on about set theory without the axiom of choice and the nature of it. Usually one doesn't want to give up the axiom of choice completely. You want to retain sort of fragments of it, like maybe you want countable choice, which means the axiom of choice for countable families. So if you have countably many non-empty sets, then you should be able to pick an element from each one of those sets. That's countable choice. But actually, many arguments that seem to involve countable choice actually involve a slightly stronger principle called dependent choice, which is the principle that says that you can make countably many choices in succession, where the later choices depend on the earlier ones that you made. So, for example, if you have a tree, say, and it doesn't have any leaves, okay, it has a root node, and there's some successors, and those have successors, and so on, but there's no terminal nodes, then, well, if there's no terminal nodes, you might want to say, well, then you can find a branch. An infinite branch, right? You just pick any successor, and then from that one pick any successor, and from that one pick any successor, and so on. Yeah? But that's not an instance of countable choice, even though it seems like we made countably many choices, because the whole tree won't be countable, maybe. Yeah. So we don't have a countable enumeration of the nodes. If we did, we could always just pick the least one in the enumeration. but I'm making countably many choices in succession, and which choices are to be made at the next step depends on how I made my choices to get to that node. Yeah, this is called the principle of dependent choice, and it's strictly stronger than countable choice. And this is the principle that you really want when you're doing measure theory. If you don't have dependent choices, then you're not going to have a good theory of Lebesgue measure. It's strictly weaker than full choice. Then the consistency assertions about the existence of those large cardinals is an analog, a kind of shadow of the hierarchy over arithmetic. So that's one way of answering your question, is that of course, if the large cardinal hierarchy is natural, then so are the consistency assertions, and those consistency assertions do form this consistency tower over piano arithmetic. So it's one way of answering. But other people object. So Steele, for example, has argued against that conception, saying, look, we don't want to replace the actual large cardinal hierarchy just with a consistency hierarchy, because for example, the consequentialist justification of the large cardinal axioms, the fact that the large cardinals are giving us all these regularity consequences for definable sets of real numbers, is evidence for the truth of the axioms, not just evidence for the consistency of the axioms. Large cardinals are giving us all these regularity consequences for consistency tower over piano arithmetic. So it's one way of answering. But other people object. So Steele, for example, has argued against that conception, saying, look, we don't want to replace the actual large cardinal hierarchy just with a consistency hierarchy, because for example, the consequentialist justification of the large cardinal axioms, the fact that the large cardinals are giving us all these regularity consequences for definable sets of real numbers, is evidence for the truth of the axioms, not just evidence for the consistency of the axioms. I mean, this is how Steele argues, that it's an instrumentalist dodge to replace the large cardinal assertion itself with the mere consistency assertion that those large cardinals exist. And so one should really think about it as a kind of a mere shadow of the real thing, but it is taking place in arithmetic. Okay, but it's not clear whether that fully answers your question, because you might have expected, look, I want a natural hierarchy of arithmetic, a genuinely arithmetic assertions, not just merely consistency assertions about set theoretic assertions. I want genuinely natural arithmetic assertions that are forming this consistency strength hierarchy. And there the situation is much less satisfactory. I mean, we have a few instances of it. We have like Goodstein's theorem that I mentioned last time, and there's other ones, and also there's sort of ordinal denotation systems. I mean, the claim that this notation system is well ordered or that one is well ordered and so on. Those ones can give you sort of these hierarchies over arithmetic, and they would have this character, a little bit of it, and so maybe that's the best kind of answer to make. But it's simply much less robust than it is in set theory. It's a great question. Any other questions? Let's see, what will be future topics for the series? Today is the last lecture of the series. It's week 8, and it's the term ending. So I'm sorry. Someone asked, when is the next lecture? But I'm sorry, this is the last lecture, and I'll put it on YouTube. So it's been a great term, and thank you all so much for coming to the lectures, and